In this video, we are going to discuss three things. First, model of molecule ethane, ethane and ethyne. Second, two molecular models of chloroethene, 1,1-dichloroethene and 1,2-dichloroethene. And last is optical isomerism of bromochlorofluoromethane.
Good morning everyone. So today I will be discussing the ability of the ethane, ethene and ethyne to rotate in organic molecules. So let me show you the model we have already made. So this is the model of ethane, and the big blue ball represents the carbon atom, while the small yellow ball represents the hydrogen atom, and the sticks represent the bonds between them. Okay, first, we all know that the bond formed in these molecules is sigma bond, and the CC bond formed is from the overlap of sp3. The rotation is able to occur because the electron density in sigma bond exists along the imaginary line between the two carbons, and the bond strength remains constant throughout the rotation. Since ethane molecule have the ability to rotate, we must identify the type of the conformation, and it is possible to identify it by using the Newman's projection. In ethane, the first one is eclipse. This happens when the CH bond in the front and the back are aligned with each other with dihedral angle of 0 degrees, which is like this. And the second is staggered conformation, which all the CH bond in the front carbon are positioned at the dihedral angle of 60 degrees relative to the CH bond on the back carbon. Next up, this is the model of the ethene molecule. The type of bond comprised in this molecule is pi bond and sigma bond. One of the CC bond is result from the overlap of the sp2 hybrid orbital from the each carbon atom. The other CC bond is a pi bond, which is result from the side-by-side overlap p orbital. Thus, this is not possible to ethene to be rotated, since pi bond are bonded sideways and is perpendicular to the plane of the sigma bond. Therefore, they cannot be rotated. So I'm going to give you an overview why the ethene model cannot be rotated. As you can see, this is a pi bond, and this is the sigma bond. So as I want to be rotated, you see there will be the intercept between the pi bond and sigma bond. Thus, this ethene model cannot be rotated. Lastly, this is the model of the ethyne. It consists of the triple bond between this carbon-carbon atom, which is 1 sigma bond and 2 pi bond. One of the CC bond is resulting from the overlap of sp hybrid orbitals, while the other 2 pi bond is formed by the side-by-side overlap of 2 unhybridized p orbital. Just like ethene molecule, ethyne also cannot be rotated because pi bond are bonded sideways. So as you can see right now, if I try to rotate it, it's much more rigid than the ethene, and it could not be rotated.
These are two molecular models of chloroethene. Now let's see if they are superimposable on each other. First, draw them freely. Do they superimpose approximately on each other? Yes, they superimpose approximately on each other. Are they the same molecule? It could be said that both of them are the same molecule. As you can see here, the first carbon is attached to chlorine atom and hydrogen atom, whereas the second carbon is both attached to the hydrogen atoms. Moving on, we have two molecular models of 1,1-dichloroethene. Now let's see if we can superimpose both of them. First, throw them freely. Do they superimpose approximately on each other? Yes, they superimpose approximately on each other. Are they both the same molecule? Yes, both of them are the same molecule. As you can see here, the first carbon is attached to the same substituent, which is hydrogen atom, whereas the second carbon is attached to the same group, which is chlorine atom. There must be two non-identical groups on each doubly bonded carbon atom to form isomers. Last but not least, we have two molecular models of 1,2-dichloroethene. Now let's see if we can superimpose both of them. First, throw them freely. Do they superimpose approximately on each other? No, they don't superimpose approximately on each other. Are they the same molecule? No, they are not the same molecule. In 1,2-dichloroethene, however, restricted rotation about the double bond means that the relative positions of substituents group above or below the double bond become significant. This leads to a special kind of isomerism. The isomer in which the two chlorine atom lies on opposite sides of the molecule is the trans isomer, named trans 1,2-dichloroethene, while the isomer in which the two chlorine atoms lies on the same side of the molecule is called the cis isomer, named cis 1,2-dichloroethene.
Both shows the superimposed molecular models of bromochlorofluoromethane. Both C atoms carry four different substituents which are bromine, chlorine, fluorine, and hydrogen. When the second model rotates, we can see that the location of bromine and chlorine are not same. It is because this molecule is a chiral and it can form enantiomers. Enantiomers is a non-superimposable mirror image molecule. It is mean that a chiral object has a mirror image that is different from the original object. To produce the mirror image, the bonds must be broken and reformed. Thus, the mirror image of the first model can be produced where the location of fluorine, bromine, chlorine, and hydrogen are same. Next, we need to exchange two atoms in one model. In this case, we change the position of bromine atom and chlorine atom. Then, we throw both models freely and observe whether these two can be superimposed or not. Both models cannot be superimposed because chlorine and bromine atom are mismatched after exchange deposition. The models are enantiomers, which are a chiral molecule. It has chiral carbon and optically active. These two molecules remain the same, therefore, it is non-superimposable. There is no second different molecule of normal chlorofluoromethane because this molecule can generate three possible stereoisomers. It has the same molecular formula and the same bonding arrangement but a different arrangement of atoms.